Hello and welcome back to Homework Help for Math 2. Today we're going to be looking at Unit 4, More Functions, More Features, which I believe was originally called Mo Money, Mo Problems, and then they decided to change it for some reason. Lesson 3, Absolutely Valuable. Starting with the Ready section, describe the transformations of y equals x squared. That's the parent function for quadratics that produce the given function. So the first problem that was assigned was number 2. So our equation for 2 says y equals, and you can see here that there's been a couple of modifications from the parent function. So we have a negative, that's one modification. So we have a negative, and then parentheses x plus 3, so that plus 3 is another modification, that's squared. And then plus 9, that's another modification. So there's basically been 3 things that have happened to the parent function of y equals x squared that have resulted in this new quadratic that will form a parabola, but it's going to look like a different parabola than the parent function. So the order matters here. So unfortunately, we can't just sort of list the 3 in any order that we want because, yeah, just the order matters. So we have to go kind of in a specific order here. And the first thing that we need to talk about is we need to talk about what's going on inside the parentheses here, which is the x plus 3. Then the second thing that we're going to talk about is going to be this negative. And then the third and last thing that we're going to talk about is the plus 9. Okay, so that's the order in which we have to do these transformations. So we have to start with our input, which is x, and then we are going to apply a scalar to the result, and then we're going to have a vertical shift at the end. So to describe the transformations, so, like I said, the first thing that we need to talk about is what's happening with the x plus 3, because that's the closest thing to our input. So the plus 3 is just, it's right. As soon as you plug in a value for x, you got to deal with the plus 3. So it's like it's the first thing that happens. And when you have x plus 3 in this context, it means that the function has been translated to the left 3 units. That's what it means when you have something like x plus 3. It's to the left 3 units. So this function is translated left 3 units. That's the first thing that's happened to it. The second thing that's happened to it is the negative. Now, the negative, it's really like -1. So it's not being stretched or shrunk in any way, but it is being flipped. That's what the negative does. It flips it. So there's a couple different ways that we can say that. So one way to say it is that it is reflected downward. Right? That's one way of saying it. We could also say it's been reflected vertically. That would be essentially the same thing. We could also say that it's reflected across the x-axis. Okay, so any of those phrasings would work in this context. The last thing we need to talk about is the plus 9, and the plus 9 is a vertical shift, so it's up or down, and because it's plus 9, it means it's up. So we can finish this out by saying it has been translated up 9 units. And that, if we apply these transformations to the parent function, we will get this new quadratic, which will result in a new parabola on our graph. Question number 4 was the next problem, and we've got a new set of directions here. Rewrite the function in vertex form, then describe the transformation on, again, the parent function for quadratics, which is y equals x squared. All right, so we got to write this in vertex form, and we saw this in an earlier unit. So in order to get this into vertex form, one way to do this, I guess technically this is not the only way to do this, but the way I'm going to solve this is by completing the square. So in order to complete the square, we first need to, we're going to be doing most of our work on the right-hand side of this equal sign. But before we do that, we need to get rid of our constant, which is the minus 10. So we actually need to bring that 10 over to the left. So we're going to start by adding 10 because in order to complete the square, we need sort of a x squared plus 4x, and then we need to kind of start with that where there's no constant on the side that has the x squared and the x on it. So on the left-hand side, we just get y plus 10. Now, to complete the square, I'm going to start on the right-hand side of the equal sign this time. So the x squared drops down and the 4x drops down. And then what we need to do is we need to add a constant. We need to kind of just create this number like sort of out of thin air almost. And the number that we want to add is going to be based on this number here of 4. It's going to be, we're going to do something to that coefficient. And the thing that we're going to do, and this is just always how we complete the square, is we're going to take that number, 4. We are going to halve it. Okay, so I want half of that number, and I want to take my result and I want to square it. Okay, so that's what's going to happen here when we complete the square. So I'll write that again just so people can see it in the actual work. Okay, so again, you take your coefficient on x, you take half of that number, whatever it is, and then you square your result. Now, the left-hand side, we had y plus 10. Now, kind of a cardinal rule in algebra and in math is that if you have an equation, if you add something to one side of the equation, in order to maintain balance, you have to add it to the other side. So there's nothing preventing us from adding this, 4 halves squared number on the right, as long as we do the same thing on the left, right? We can't just randomly add a number on the right and then not do anything on the left. Then the equation's no longer balanced. So whatever we do on the right, we have to do on the left. So I'm also going to add 4 halves squared, which I could simplify, but I'm just going to leave it like that for right now. All right, so let's clean this up a little bit. So on the left, we have y plus 10 plus 4 halves squared. Well, 4 halves is 2, and 2 squared is 4. So we really, on the left, we have y plus 10 plus 4, which means we have y plus 14. All right. Now, on the right-hand side, the whole reason why we're doing this kind of weird thing on the right is because I want to be able to write this quadratic as a binomial squared. That's the whole point of completing the square. And what this quadratic on the right, what it turns into when you write it in this form, the first term is going to be x. And we're going to be adding the number that goes here is this number, is the 4 over 2, right? Not the squared, but just the 4 over 2 part. So 4 over 2 is 2, so this becomes x plus 2. That's basically the process of completing the square. And then in order to put this into vertex form, we're going to bring that plus 14, we're going to now bring it over to the right. So we're going to subtract 14 on both sides. So our answer here, our vertex form, is going to be y equals, I've got my binomial squared, so x plus 2 squared. And then, again, we got rid of that 14 on the left, so it came over to the right as a minus 14. And that is the same thing as our original equation. It just looks different, but it's the same thing. The first one is in standard form, I think it's called standard form. And the one that we just wrote is the same function. It's the same graph. It's just in vertex form, y equals parentheses x plus 2 squared minus 14. Now, the other part of this question is description. So for number 4, the function, go ahead and change the size here. So if we look at sort of what has happened to this equation based on the parent function, well, the first thing that we need to talk about is this x plus 2 piece. Right? So we're first going to talk about the x plus 2, and then the second transformation is the minus 14. But we got to start with the x plus 2. So when you see something like this, when you see x plus 2 on really impacting the input here, it's having a pretty direct impact on whatever your x value is, or rather what's inside the parentheses. So when you see that, that is an indication. Oh, hold on. Go away. There we go. Okay, cool. So the first thing that's happened here is that the function has been translated left 2 units. So again, when you see plus 2 on your x, that means that the whole thing has been shifted to the left some amount, and in this case it's 2. So it's been translated left 2 units. And we have minus 14. So the minus 14 tells us that it has been translated down 14 units. So from the parent function, which again was up here, we've taken that graph and we've gone to the left 2 and down 14. Moving on to the set section. Directions here say, use the given function rule to fill in the table of values. And we're going to start with number 8. So for number 8, this problem's relatively straightforward. It's giving us a formula for this function. So f of x equals absolute value of x plus 1. So just saying whatever your input is, take it, add 1, and then take that number and just provide the absolute value of your result. So let's just go ahead and plug them in. So our first x value is negative 2. And for f of x, so f of negative 2, negative 2 plus 1 is negative 1. And then the absolute value of negative 1 is 1. And again, I'm not going to do this for every single problem, but maybe I'll just do it once so we can actually see it visually. So we have absolute value of negative 2 plus 1. And negative 2 plus 1 is negative 1, and the absolute value is 1. So continuing on, for negative 1, so f of negative 1, we take negative 1, we add 1, we get 0, and the absolute value of 0 is 0. Our next input is 0, so when we take 0 and plug it in, we get 0 plus 1 is 1, and the absolute value of 1 is 1. When we take a 1 and plug it in, we get 1 plus 1 is 2, and the absolute value of 2 is 2. And our next input is 2. We take a 2, we plug it in, we get 2 plus 1 is 3, and the absolute value of 3 is 3. And that's it for that problem. Number 9, pretty similar to number 8. We, again, have a function here. We have an explicit equation. We've got a little absolute value that we got to deal with, and we're going to plug in our inputs from negative 2 to 2. So for the first one, and I'll write out the first one, but I think that'll be the only one that we're going to have to write out. So for h of -2, our first column that we have to fill in, is we're going to take our function and we're going to replace x with -2 and plus 1. Notice that I'm rewriting it exactly the way that it appears, right? This is not, the absolute value does not include the 1, right? That would be a different function. So the plus 1 is outside the absolute value. So we just have to simplify this a little bit. The absolute value of -2 is 2, and when you add 1 to the result, you get 3. So you plug in a -2, and you get a 3. For -1, you plug in a -1. The absolute value of -1 is 1, and then 1 plus 1 is 2. Plug in a 0. The absolute value of 0 is 0, and 0 plus 1 is 1. Plug in a 1. The absolute value of 1 is 1, and 1 plus 1 is 2. Take a 2. Absolute value of 2 is 2, and 2 plus 1 is 3. Next assigned question is 11. We've got a new set of directions here. Show how the graph of the given function would change if absolute value was applied to the entire original function. Sketch on top of the given graph and indicate where the new function would be the same and where it would be different. So we have a graph of a function. This is clearly a linear function. And currently, this graph does not really reflect any kind of absolute value concept. And the question is asking, well, what if we do apply absolute value to this? So the whole idea behind absolute value, the sort of formal definition is that it's the distance from 0. But we sort of commonly just think of it as non-negative. Right? So either 0 or positive. Right? 0 is neither positive nor negative. So when we say non-negative, it just means it's either positive or it's 0. So in order to complete this, all we really need to do is say that the portion of this graph that is positive is going to stay the same. And when I say positive, I mean the y value, right? So where this value, the y value, wherever it's positive, that's actually not going to change at all when we apply absolute value to it, because the absolute value of a positive number is again a positive number. So nothing really changes when you apply the absolute value to a positive result. Where it is going to change is going to be where y is negative, because when you apply absolute value to a negative, you change it and it becomes positive. So this piece right here is not going to change, because the absolute value of all of those results is already positive, or it's going to stay positive. Whereas this piece, because my y values for that piece, they're currently negative, but if I apply absolute value to that, they're going to become positive. So essentially what's going to happen is that red, the piece that's circled in red, is going to come up here, right? And just as a quick sketch, it's going to look something like that, right? Now I'm gonna fix it a little bit so that it looks a little bit nicer, but we would expect our final result to look something like this, because what's going to happen is all of these values here on this line, the magnitude is not going to change at all, but it's going to become positive. So go ahead and clean this up a little bit. So to graph this, notice that we're going to keep that point right where it is. And if we want to graph this, and be somewhat precise with it, I think it might be good if we identify the slope, because we have a straight line here, and as soon as we get the slope, graphing this is going to be, pretty straightforward. So the slope here, we could pick any any 2 points will work. I'll just pick those 2 points right there. And so notice that my rise is 1, 2, 3, 4, 5. It's going down, but that's irrelevant for absolute value purposes. So my rise is 5 and my run is 2. So my slope here is 5 halves. And the slope of the original function is negative, negative 5 halves. So when the negative piece of my graph here, and I guess I'll do this. It says to, sort of trace over the existing graph. So I'll go ahead and do that. So that green piece right there, that is part of my absolute value graph. It doesn't change. But now from here, I want to go back up. It's going to make like a V shape. So now my new slope, we'll say m prime, is going to be positive 5 halves because I don't want to go down anymore. I want to go up. So again, from that point right there, if I go up 5 and over 2, that brings me to there. So, and if I do it again, that brings me to there. And so if I complete my graph, I get that. And so the green line here represents the graph of this function if we apply absolute value to the entire thing. And also notice that another way that we could have done this is simply take all of our points on the bottom part of the original graph and just flip the number. So here you could see that was negative 5. Well, notice that it became positive 5. And notice that down here we had a negative 10. Well, that became a positive 10. So we also could have just done it that way, and that would have worked. So we're done this problem. I think so. Let me just double check. Sketch indicate. Yeah. So we're pretty much done this problem. Just for completeness' sake, notice that this graph is the same when x is less than or equal to negative 2. So when x is less than or equal to negative 2, the graph did not change at all, but it is different when x is greater than negative 2. So just to clarify that. Also, the question did not ask this, so this is extra, but if you were wondering what the original function was f of x equals, our slope was negative 5 halves x, and our original y-intercept was negative 5. The new function is simply f of x equals that same thing, right? Nothing actually changes except we put an absolute value around the entire thing. And that is represented by the graph that's in green. Question 12. So for question 12, it's the same general idea as 11. And we're taking this linear function, and we are applying the absolute value function to it. So again, with absolute value, whenever our result is positive, nothing really changes. So the part of this graph that is above the x-axis is not going to change. So it intercepts the x-axis there at 4. When x equals 4, we get 0. And so we can see that the portion of this graph that's to the right is still going to be it's going to be the same graph when we apply absolute value. So again, I'll do the graph of the absolute value in green. And so this piece of my graph is still going to be there. So we'll just kind of leave it. That's off a little. Let me read. It's going to bother me. Let me do it one more time. It's not erasing. I don't know why. 1 second. All right. So we're going just like that. Good enough. So that piece is not going to change. The part that is going to change is the part of this graph that is below the x-axis, because when you apply absolute value to a negative, you get a positive. I'll do this in a different way than 11. We kind of talked about this at the end of 11. So one way to sort of, quote unquote, fix the graph so that it actually is absolute value is you could just take any of your point, like I can take this point here and just flip it across the x-axis. So right now it's at 0, -1. When I flip it, it's going to become 0, +1, right? Because the absolute value of -1 is 1. The next point looks like it's right there. Right, because the slope is 1/4. So at -4, we get -2. Well, with absolute value, that -2 is going to become a +2. The next point is right there, which is at -13. And at -13, the original function gave us a -3. The absolute value of -3 is +3. So our result, our output of this function, is no longer -3, but now it's going to be +3. And you can see that this piece is also forming a straight line, which we would expect. And so we just have a straight line going through all of this, and looks like that. So the graph of our absolute value function is the piece that's in green. It is a V, it's just kind of a flattened V. That's basically it for this problem. But again, the directions did say, where is it the same and where is it different? So just for completeness' sake, this graph is the same. Right? The graph of the absolute value function, the part that's in green, it's the same when x is greater than or equal to 4. So once you hit 4 and you go to the right, nothing really changed. But it is different when x is less than 4. So if you're to the left of 4 on the x-axis, it is now above the x-axis instead of being below the x-axis. And this part, again, this wasn't strictly necessary, but it's not too difficult to see that the original function, which again was linear, so f of x, the slope of the original linear function was 1/4 x, and the y-intercept of the original function was -1. That's the black line that was on that graph at the very beginning. The new function that has absolute value, nothing changes with the original function. It's still 1/4 x minus 1, except now there's an absolute value around it. And that, if you graph that, you will get the graph that is in green, which kind of looks like a V. We'll wrap up this assignment in the Go section. And the directions here say, evaluate each expression for the given value of the variable. So we're going to start with number 14. So with 14, our expression is -s. So it's a relatively simple expression. There's a grand total of 2 symbols. There's a negative sign, and then there's a variable of s. And basically this is just saying, all right, well, what do we get when s equals 4? And this might be a little overkill, but I think it's a good habit to get into, is when you're evaluating algebraic expressions, I think it's a good idea to use parentheses anytime you are substituting a number for a letter. So what that means is, for 14, what I'm going to do is I'm going to rewrite -s, but as soon as I see an s, I'm going to do an open set of parentheses, and then I'm going to plug in my value for s. So what that means is I have my negative, okay? That's the negative in front of the s. Let's get rid of this underline right there. So I have the negative. Now I get to the s, because it's negative s. And because I'm now plugging in for s, I'm going to do open parentheses. Now I'm going to plug in what s is. So for number 14, s is 4. So I'm going to put a 4 there, close parentheses. And then that's it, because my entire expression is just negative s. So I have negative parentheses 4. Well, now I no longer need the parentheses, right? They sort of helped me plug them in, but they've kind of outlived their usefulness at this point. And when you give your final answer, you typically want to use the fewest number of symbols possible. So now the parentheses are like no longer necessary. So this piece just becomes negative 4, and that's my final answer. Next question is 15. Our expression is negative t. So again, just a grand total of 2 symbols, negative and a letter. And this time I want to know, all right, well, what happens when t is negative 7? And again, just like with 14, I'm going to rewrite my expression, which starts with a negative. Now I've encountered the t. I've encountered the thing that I'm going to plug in. That means I'm going to introduce a set of parentheses here. Now in this case, t is negative 7. So I'm going to plug in a negative 7, close parentheses. And that's it, because our expression is negative t. So now all I have to do is clean it up. Again, now the parentheses aren't really necessary anymore, and I have a negative of a negative. Well, a negative of a negative is positive, and I certainly don't need to say plus 7. I can just say 7, and that is my final answer. 16. My expression is negative x, and I want to know what happens when x equals 0. So I have negative. Now I've encountered the x, so I do open parentheses, plug in my value for x, and then close the parentheses. I no longer need the parentheses, and negative 0 is the same thing as 0. And as always, if you can get away with giving your answer in fewer symbols, do it. In general. So this is all just 0. That's my final answer. Next assigned question was 18. So with 18, my expression is the absolute value of v. So I'm going to rewrite that. So I'm going to start with my absolute value. I've now encountered the v. I've encountered the thing that I'm going to be substituting for. So I introduce a set of parentheses, and now I write my number, which in this case is negative 25. I close the parentheses because I'm done substituting for v, and then I close the absolute value. So now, again, the parentheses are no longer necessary. So I have the absolute value of negative 25, and the absolute value of negative 25 is simply positive 25. Don't need to say positive. We can assume that that number is positive. So for our final answer for 18 is 25. 19. For 19, our expression is negative parentheses a. So I'll tell you right now, for 19 and also 20, we're going to end up getting it's a little redundant in terms of the parentheses, and they're not strictly necessary. So 19 might initially look a little bit more complicated than it needs to be, but I'm going to do it anyway because, again, I think that introducing parentheses when you plug something in is like important, even though in this case it's going to be a little, well, you'll see. So with 19, our expression starts with a negative. Then our expression includes parentheses. Okay. Now I've encountered the a. Because I'm plugging in for a, the way that I would do this is I would actually do a second set of parentheses. And this is kind of what I mean by it being a little redundant, but it's going to work out. So now I've encountered the a, so now I'm going to introduce parentheses. I'm going to write my number, which is negative 25, and I'm going to close the parentheses because I'm done plugging in for a. Now I go back to my expression, and my expression has a closing set of parentheses in it. So we're just being very precise and methodical here. So the inner set of parentheses is just negative 25, so that is fine. And then I want the negative version of that. I want the negative version of negative 25. So a negative of a negative is a positive. And so all of my parentheses go away, my negatives go away, and I get positive 25 for number 19. All right, number 20. So if you thought that there were redundant parentheses in 19, well, I've got some good news for you because they're going to come back for number 20. So for number 20, my expression is negative parentheses, negative n, close parentheses, and I want to know what happens when n is negative 2. So we have a negative out front. That is there. And then my expression has a parentheses, so I'm going to include that. Then my expression has a negative in front of the n, so I include that. Now I've encountered the n. Now I'm going to be plugging in for n. Again, I think it's a good idea to introduce a set of parentheses anytime you're plugging it in. So because I'm plugging in for n, I'm going to introduce my own set of parentheses. And the number that we're plugging in is negative 2. Now I'm done plugging in for n, so I'm going to close that set of parentheses. And then in my original expression, the thing that follows the n immediately is another closing set of parentheses. So what I have is I have this kind of funky looking thing here where I've got the negative, negative, negative 2. All right, well, the negative 2 inside the inner set of parentheses is just negative 2, and then this negative right here causes this negative to essentially go away. And as an intermediate step, what I kind of have right now is I have negative parentheses 2. Right? So the two negatives on the inside sort of effectively cancel each other out because a negative of a negative is a positive. But I still have the original negative, which is here, right? That negative is this negative, which is also this negative, right? So my sort of final thing over here on the right is I have negative parentheses 2, the parentheses go away, and my final answer is just negative 2. So I don't think it's too difficult as long as you can just sort of go step by step by step. It's relatively straightforward. You just got to be careful when you're plugging in and making sure that you don't miss any of your symbols.